Welcome to the supplemental video introducing our work, Time-Variant Vector Field Visualization for Magnetic Fields of Neutron Star Simulations. Let me briefly explain the physical background before we look at the visualization tool. The strongest magnetic fields in the universe can be found within neutron stars, potentially playing a role in initiating astrophysical jets and facilitating the outflow of neutron-rich matter, ultimately resulting in the production of heavy elements during binary neutron-star mergers. Since such effects may be dependent on the strength and configuration of the magnetic field, the formation and parameters of such fields is part of current research in astrophysics. Magnetic fields are investigated using simulations in which various initial configurations are tested. However, the long-term configuration is an open question, and current simulations do not achieve a stable magnetic field. Our visualization tool enables physicists to interactively explore the generated data. To interactively analyze the simulation datasets, we have developed four main tools that allow domain experts to explore the evolution of the magnetic field in real time, which I will introduce in a moment. Here, we see the tool at the beginning. Nothing is visible at first, but we can navigate intuitively, as we are used to from 3D tools. To gain an insight into the magnetic field, we first switch on the cross-section tool. This tool creates a plane on which the cross-section of the magnetic field is visualized. We use line integral convolution to display the field densely. Now we can move the plane and the visualization updates accordingly in real time. We use this plane to find an interesting spot in the magnetic field. Once we have found an interesting area, we can now select the seed selection tool. This allows us to place seed points on the plane where streamlines are generated directly. We can place several seed points at the same time. This gives us an impression of the magnetic field in 3D and allows us to view specific areas. As we are interested in the evolution of the magnetic field, we can now look at different time steps. There is a time slider that allows us to select any time step. The visualization adapts automatically and the streamlines are regenerated. As some structures only become visible when we see a sequence of time steps, we can also play the time slider. We can set the speed if we want to take a closer look at a time interval. Now we realize that in some time steps, the magnetic field is very turbulent and chaotic. We can change the appearance of the streamlines by activating the streamline tool. Let's take a look at time step 280, where occlusion makes it difficult to see how the magnetic field is structured. We can set the streamline display to transparent, and the structure becomes immediately clear, and we can even identify 3 vortexes that are located in the vector field. By pressing the play button, we can now also observe how the vortexes develop. After some time, the turbulence of the magnetic field subsides, and the transparent view can be reset to opaque. Now we can make further settings to display the streamlines. Instead of solid lines, we can display them as arrows. This allows us to see the direction of the field. We can set the length and density of the arrows. We can also animate the arrows to improve the perception of the direction. We can use dashed lines, which show the direction more subtly than the arrows. By default, the color of the streamlines is determined by pseudo-chroma depth, depending on the camera position. Here we can set the depth of the effect. It is interesting for astrophysicists to know which areas are inside and outside the neutron star. To do this, we can use the interface tool to switch on the surface of the neutron star. Alternatively, we can set the color of the streamlines to indicate whether a part of the streamline is inside or outside the neutron star. This concludes our introduction to the visualization tool for magnetic fields of neutron stars. Thank you for your attention.